Chapter 2, number 52. Two cars drive on a straight highway. At time t equals 0, car 1 passes mile marker 0, traveling due east with some speed of 20 meters per second. At the same time, car 2 is at 1 kilometer east of mile marker 0, traveling at 30 meters per second due west. Car 1 is speeding up with an acceleration of magnitude 2.5 meters per second squared, and car 2 is slowing down with an acceleration of magnitude 3.2 meters squared. Write x versus t equations of motion for both cars, taking east as the positive direction, and at what time do the cars pass each other on the road. So we'll have now two roads. So I'm going to have a blue car and a red car. Two roads just so they don't hit each other, which is potentially possible at least. And car 1 at time equals 0. Car 1 is at x equals 0. And I'm going to call this, and the names will get mildly weird, x1, 0. In other words, the time of the position of car 1 at time equals 0. And that is 0 at time equals 0. And then it moves on as life goes on. It has, of course, has an original velocity, which I'm going to call v1, 0. And it has some acceleration, which points eastward, and I'm going to call that a1. And we have numbers for a lot of these things already, but that's what we've got. And then down here on a different road, we've got car 2, and car 2 starts off somewhere and then moves over. And the idea is that this is x2, 0. x2, 0. And we know that that's going to be 1,000 meters because of the 1 kilometer. But it's moving westward at v2, 0. And it has an acceleration, and this is kind of key to keep in mind here. The acceleration is also eastward because it's getting slower. So its acceleration has to be opposite to its velocity. So that's our picture, which occupies a lot of space, but that's okay. And then what we say is for car 1, we know that the position at any time, x1, is going to be where it started, x1, 0, plus its initial speed, v1, 0, times t, plus 1/2 times a1 times t squared. And we know that for car 2, we're going to have x2 is x2, 0, plus v2, 0t, plus 1/2 a2 t squared. And it's just going to be messy, but we'll be able to do it. So I'm going to go, we'll leave behind the problem for a second and just give us some more space to write. And we're left with x1 is 0 plus 20 meters per second times t plus 1/2 times the acceleration, which is given as 2.5 meters per second square, times t squared. And then we have that x2 is going to be the initial position, which we know is 1,000 meters, plus its initial speed, which is 30 meters per second, but in the minus direction, times t, plus 1/2 times the acceleration, which happily here is 3.2 meters per second square, also times t squared. So these are the equations of motion for x versus t for each of them. And then part B says, at what time do the two cars pass next to each other? And to here, since this is the position of x1 at any time, and this is the position of x2 at any time, then they will pass when, so we'll say they pass at the t such that x1 equals x2. So in principle, we could go back up here and just set these two things equal to each other and do some particularly heinous algebra and end up with a time. I'm not going to do that because this is not a math class, it's a physics class. We can use other tools. In algebra class, they'd want you to solve this quadratic equation. It isn't fun. It isn't terrible. No, that's not true. It's actually pretty terrible. It's just the quadratic formula, but it's kind of gruesome. Instead, what I'm going to do is remember that equality in algebra, in other words, this bit, is the same thing as intersection in geometry. So I'm going to just sketch what these guys have to look like. So the first guy, the blue car, has a positive slope at the start and opens upward, but starts through the origin. So the starting through the origin gives me that. I'm coming through the origin with some positive slope, but then I have to slope upward. I have to curve upward. So it might look something like that. And then the red guy starts at 1,000, but is coming, as we can here, coming down as a negative, but is still curving upward. So comes in with some steeper line and then goes up. I actually don't like that particularly well, so I'm going to go back and change a little bit. I'm actually going to go back and change the blue as well. No, this will be fine. Comes in steeply and then goes out. And this value of t, whatever it is, would be the time. To actually do that, I'm going to have to graph it. So I'm going to go over to Desmos and graph it on Desmos and then see what comes back. The way we do that in Desmos is type in the formulas as shown on the left there. Desmos does require one little bit of complication. Desmos can only really plot y versus x. It can't really handle t, or rather it can, but it's a little bit more complicated and means something a little bit different. So I had to define these things as functions of x here, but notice that every function of x is really, for our purposes, this is really a t. Oops. This is t, and this is t, and this is t, and so on. Oops, and I guess it got cut off, but there's a t square out there. And that gives us our two things. The other thing that comes out that's kind of weird, and it's just like a Walker weirdness, is that the physical setup for the problem is kind of strange. If one car is slowing down from 30 meters per second to 0 or to whatever at 3.2 meters per second squared, it's going to come to rest. And if this is a car, it's going to stay there. It doesn't suddenly go back the other way. I guess theoretically the driver could instantaneously throw the engine into reverse at exactly the same acceleration, but that's really not physical. And so he's being a little facetious because he wants you to produce this graph, but he chose time values that are after the stopping point, which is just kind of strange and really isn't. I don't think it was intentional. I think he made up the problem and didn't actually notice that it was weird. So what would actually really happen is the driver would almost certainly stop at this point. And so this whole part of the graph is wrong. So I asked Desmos to sort of show me what that would look like, and it looks like, well, the following. The scale's a little different, so the curves look a little flatter, but they aren't really. And most importantly, what we see is that now the place where they meet is here. So they meet at a time of sort of 19-ish seconds rather than the 20-something second from before. This is really exceedingly extra detail. If you were an engineer, you'd have to worry about stuff like this. But for us as an introductory class, this would be not. I would make sure that a tested problem didn't have this extra layer of complication in it. Just a little bit much to see under a time pressure. But it's good if you did notice that it's kind of weird the car stops and starts reversing. And this is sort of the physical thing that would come out.